Hello, welcome back to Discrete Calculus with Wolfram Language. I'm Alistair Forsyth, and this lesson will be about summing finite series. So to get started, we have to go over sigma notation, which is what we use to describe the sum of finite and infinite series. Here, we have an example of a finite series written using sigma notation. The I in this expression is the index of summation, whereas the 0 and 5 are the lower and upper bound of summation. Altogether, this expression describes the sum of the integers from 0 to 5. Oftentimes, we'll sum functions of our index or elements of a list that use our index. Here, we have examples of both of these cases, the first summing x of I from I equals 0 to I equals 5, and the second summing x sub I from I equals 0 to I equals 5, with x on the left being a function and x on the right being a list. Along with that, it can also be helpful to change the step size of the index. Now formally, the step size of the index using sigma notation is statically 1. However, we can achieve the effect of a different step size by changing what the index itself is. For example, on the left, we have the sum of x sub I from I over 3 is equal to 0 to I over 3 is equal to 3. This has the effect of taking I over 3 is equal to 0, so I is equal to 0, then I over 3 is equal to 1, so I is equal to 3. Then I over 3 is equal to 6, so I is equal to 2. And then I over 3 is equal to 3, so I is equal to 9. Therefore, the sum takes the sum of x sub 0, x sub 3, x sub 6, and x sub 9. Alternatively, on the right, we have the sum of x sub 3i from I equals 0 to I equals 3. Similarly, this achieves the effect of summing x sub 0, x sub 3, x sub 6, and x sub 9. Altogether, this will end up being our standard form for the sum of a finite series, with I naught and I max as our lower and upper bounds respectively, x sub I as the elements that we're summing, and I over c as our index. Now, we can write out any sum of this form in the Wolfram language as sum brackets of x sub I, comma, I naught, comma, I max, comma, c. If we do that with the sum we had earlier, taking sum of I, 0, 5, we get 15, which makes sense because 0 plus 1 plus 2 plus 3 plus 4 plus 5 is 15. Finally, I want to note here that some writers will use alternate notation for the bounds of summation. Some authors use the notation on the left, summing up all the indices of x sub I, where I is an element of some larger set, big I. Alternatively, some authors use the notation on the right, which takes the same process but specifies the bounds in a different location. Now that you've got a feel for reading sigma notation, we can look at some basic manipulations of finite sums. To start with, sums follow the associative property for multiplication. So if we take the sum from I equals 0 to I equals n of c a sub I, it'll be the same as c times the sum from I equals 0 to I equals n of a sub I. Similarly, sums also follow the associative property for addition. So if we take the sum of I equals 0 to I equals n of a sub I, and then add that to the sum from I equals 0 to I equals n of b sub I, that will be the same as just taking the sum from I equals 0 to I equals n of a sub I plus b sub I. Along with that, they also follow the commutative property for addition. So when you take the same list a sub I, going through its elements from I equals 0 to I equals n is the same as going through its elements from n minus I is equal to 0 to n minus I is equal to n. Finally, we have an identity that follows from these properties. If you take the sum from I equals 0 to I equals n plus 1 of a sub I, that will be the same as taking a sub 0 plus the sum from I equals 1 to I equals n plus 1 of a sub I, or it'll be the same as taking the sum of I equals 0 to I equals n of a sub I plus a sub n plus 1. Overall, what this last manipulation is doing is just changing the bounds of the summation and then taking the last or first element out of it. From here, we can use these manipulations to establish rules for common sums. For example, when computing the sum of an infinite series, we can start with the general form S is equal to the sum from I equals 0 to I equals n of a plus bi. Then we can apply the commutative property, changing our index to n minus I. We can then add those two forms of the same sum and then divide by 2 to retrieve another form of that sum. This process will retrieve for us s is equal to 1 over 2 times the sum from I equals 0 to I equals n of 2a plus bn, which we can then simplify to s is equal to 2a plus bn times n plus 1 divided by 2. Notice that because 2a plus bn does not depend on I, we can treat it as a coefficient and move it out of the sum. Now this gives us our first rule as the sum from I equals 0 to I equals n of a plus bi will be equal to 2a plus bn times n plus 1 divided by 2. Moving on, we can also compute the sum of a geometric series. We can start with the form s sub n is equal to the sum from I equals 0 to I equals n of a times b to the power of I. Then we can observe that s sub n plus a times b to the power of n plus 1 will be equal to a times b to the power of 0 plus the sum from I equals 0 to I equals n of a times b to the power of I plus 1. From there, we can observe that s sub n plus a times b to the power of n plus 1 is then equal to a plus b times s sub n. At that point, we can just move a couple terms around and get s sub n is equal to a times b to the power of n plus 1 minus 1 divided by b minus 1. Overall, this establishes our next rule as the sum from I equals 0 to I equals n of a times b to the power of I is equal to a times b to the power of n plus 1 minus 1, all divided by b minus 1. Now to add on to this list, we can include the rules. The sum from I equals 0 to I equals n of 1 is equal to n. The sum from I equals 0 to I equals n of I is equal to n times n plus 1 divided by 2. Notice that this is a special form of a plus bi, where a is equal to 0 and b is equal to 1. Similarly, we have the sum from I equals 0 to I equals n of I squared will be equal to n times n plus 1 times 2n plus 1 divided by 6. And then the sum from I equals 0 to I equals n of I to the power of 3 will be n times n plus 1 divided by 2 squared. Often, it's helpful to nest one sum inside of another to compute a more complex summation. Here, we have an example of a double sum, taking the sum of a value of a function at each 1 by 1 tile in a 10 by 10 square. This ends up looking like the sum from x equals negative 5 to x equals 5 of the sum from y equals negative 5 to y equals 5 of f of x comma y. To see why this would be helpful, say we wanted to calculate the volume of a house with a gabled roof centered at its midpoint. Let's say the roof has an angle of 60 degrees and the house has a 20 by 20 unit base centered on 0, 0. Using that information, we can derive the function f of x, y, is equal to 10 minus the absolute value of x times the tangent of 60 degrees plus 10. We could then estimate the volume of the house using a double sum. If we take the sum from x is equal to negative 10 to x is equal to 10 of the sum from y is equal to negative 10 to y is equal to 10 of f of x comma y, that will give us an estimate of the volume of the house. Plugging this all into the Wolfram language, we can see that our sum will retrieve 8,047. To calculate our percent error, we can use some geometry. The base of the house will just be a rectangular prism. That'll be 20 by 20 by 10 wide. Now the roof of our house will just be a triangular prism, which we can calculate by taking 10 times the tangent of 60 degrees, which will be the height of that triangle, times 20, which will be the width, times 10, which will be the base divided by 2. From there, we can add the volume of the base and the roof to get the total volume of the house, which is 7,464. Now this looks like a large gap in the two volumes, but it's actually a percent error of only about 8%. Now I think this is really cool. Even though I would stick to geometry for this problem in particular, what this shows us is that with a relatively small margin of error, we can calculate the volume of any surface for which we know the height as a function of its base. what if f of xy was sinusoidal on both x and y? Or what if it varied sinusoidally with x and with a polynomial of y, or with an exponential of y? Off the top of my head, these are really difficult things to figure out geometrically. However, with a double sum, we could get an estimate of the volume with very little effort. Now, when using double sums in the real world, it can often be very helpful to interchange the order of the inner and outer indices. Something that's very convenient is that when neither index relies on the other, we can just swap them. As a result of the commutative property of addition, if x does not rely on y, 0 doesn't rely on 0, and n doesn't rely on k, the order that we do this sum in literally does not matter. Another especially convenient case are when one's bounds are defined by the other, but we can just move them using inequalities. Now this won't work all the time, but if we're given a case like the sum from x equals 0 to x equals n of the sum from y equals 0 to y equals x of f of x comma y, we can then write out the bounds using 0 is less than or equal to x is less than or equal to n, and then 0 is less than or equal to y is less than or equal to x. From there, we can merge these into one inequality. 0 is less than or equal to y, which is less than or equal to x, which is less than or equal to n. We can then separate this back out again and retrieve 0 is less than or equal to y is less than or equal to n, and then y is less than or equal to x is less than or equal to n. This retrieves for us the sum from x equals 0 to x equals n of the sum from y equals 0 to y equals x of f of x comma y is equal to the sum from y equals 0 to y equals n of the sum from x equals y to x equals n of f of x comma y. Now this will not always be very convenient, but generally when given the minimum value of x is less than or equal to x is less than or equal to the maximum value of x, and y naught as a function of x is less than or equal to y is less than or equal to yf as a function of x, we look to find the functions x naught of y and xf of y such that the sum can be preserved by the minimum value of y is less than or equal to y is less than or equal to the maximum value of y, and then x naught of y is less than or equal to x is less than or equal to xf of y. Now, this was a fairly short lesson. However, in it we covered sigma notation, some properties, rules, and common forms of finite sums, and double sums. In the next video, we'll go over summations of infinite series. Again, I'm Alistair Forsyth, and thank you for watching. Bye-bye.